so let's get started here. So this chapter, we're going to move on into the next chapter, chapter 14 in our textbook, entitled Conjugated Dienes. And importantly, this chapter is going to give you a little bit better of a sense as to what the future is going to look like in this course, where you come in and we introduce a new functional group. We talk about how to name that functional group, the properties of that functional group, and lastly, reactions of those functional groups. And then we move on to the next. All right? We're going to pick this apart here. We'll talk about what this word conjugated means here in a second. And then our second word here is diene, E-N-E. What does that remind everybody of functional group-wise? Alkenes, all right? So now if we're talking about dienes, we're going to be talking about molecules that contain more than one carbon-carbon double bond, okay? But before we go on to talk about dienes, we're going to use this as an opportunity to just review nomenclature for our alkenes, and then we'll build off of that from there, all right? So we're going to start with a simple alkene here, and we're going to go through our steps that we laid out last week for, I guess, 2 weeks ago for our nomenclature, and we're going to update those rules. All right, so first we said that we're going to find our parent chain in our molecule, our longest continuous set of carbons. So we got to update this here. Now that we have a functional group, that carbon-carbon double bond in our molecule, we're looking for the longest continuous set of carbons that contains that functional group. All right, so important caveat to add there. Whenever we have a functional group in our molecule, our parent chain must contain that functional group. All right, and since we have a new functional group, we have a new suffix here, alkenes. Use that E-N-E ending. All right, so my longest continuous set of carbons necessarily containing that carbon-carbon double bond would be these four here. Using that same number of carbon prefix but, but changing my suffix, this would be butene. All right, our second thing was about finding and naming our substituents in our molecule. And here we got nothing new to add. All right, same exact procedure that we laid out before for finding and naming substituents. We get to step 3 here, the numbering of our molecule. This we are going to have to update here. All right, again, we want the lowest possible number in the name. Okay, but now that we have this functional group, we're going to prioritize that functional group when numbering. Meaning I don't really care about any substituents in that molecule. I just want to make sure that the functional group itself has the lowest possible number in the name. All right, and then lastly, when we assemble our name, we now need to also include the locant of our functional group. Okay, so taking a look at this alkene here, I'm going to number in such a way that I make sure that double bond has the lowest possible number. You can see for alkenes, they're, for obvious reasons, located between 2 carbons. All right, we always refer to the location of that carbon-carbon double bond by whichever number is smaller. All right, so specifically for our carbon-carbon double bonds, we use that smaller locant. So this molecule here is said was butene, but we got to indicate the location of that double bond. This would be 1-butene. All right, so we took those same 4 steps that we had laid out for nomenclature previously, and we've added to them for now our new functional group, our alkene. Let's take these and put them into practice here. I'm going to do these 2 examples for me. All right, so this first one here, how many carbons we got in our parent chain? 5. All right, I tried to be tricky, and everybody was going to want to just say these 6 across here. But again, looking at this molecule, the one thing I know right off the bat is that these 2 carbons must be a part of that parent chain. Your parent chain must contain that carbon-carbon double bond. So my longest continuous set of carbons would be these 5 here, meaning that this would be considered an ethyl group. And I'm going to number in such a way that prioritizes that carbon-carbon double bond, making sure it gets the lowest possible number. So my ethyl group here is located on carbon 2, 2 ethyl, 1 pentene. All right. One other name that would be, what's up?
Would it be okay to not put the 1 on the pentene because it's safe to assume that's going to be on the first one? Or
No, it could, no, because I could move that double bond back here and all of a sudden it's a different molecule, right? So no, we even if it's on carbon 1, you can't just assume it's on carbon 1. It couldn't be on carbon 2, 3, et cetera, et cetera. There is another way that I could write this name that would be perfectly equivalent, although it's got all that same information in there. And it's a little bit weird, although in some circumstances we have to do it, and so we'll see that in the future. You can always move the locant of the functional group back right before the functional group suffix. So what would be equivalent, what I would be allowed to do, is to instead say 2-ethyl and then pent 1-ene. All right, where again, the location of that functional group, carbon 1, I've moved directly in front of that ene suffix. All right, both of these are perfectly acceptable names. Again, sometimes we're going to have to do this, and we'll see that in the future. Okay? All right, cool. So again, parent chain must contain that carbon-carbon double bond. In this one, my parent chain is pretty straightforward. All right, but when it comes to numbering our parent chain, let's look carefully. All right, which one of these two numbering schemes do I want, the red or the blue? The red, because I'm not going to pay attention to these chloro substituents at all when I'm picking my numbering scheme. The only thing I'm going to look at is that functional group. We prioritize that functional group, making sure our functional group has the lowest possible number. That's why I'm going to pick my red numbering scheme here. All right, as we said, these are chloro groups. Remember, when we build this into our name, we're going to need the locant for both of them, so 6,6-dichloro. My carbon-carbon double bond I'm going to refer to by which of these two numbers? The 3. So dichloro 3-heptene. All right. Or I could have said 6,6-dichlorohept3-ene, again, where we move that locant of that double bond to right before its suffix. Cool. So again, we prioritize our carbon-carbon double bond when we're picking our numbering scheme. Now, this molecule is not quite done here. There's an important piece of information that's missing from the name of this molecule. All right? Let me get rid of my color coding real quick so you can see maybe a little bit easier. Okay. The important thing that we got to keep in mind here is that our carbon-carbon double bonds, unlike carbon-carbon single bonds, cannot rotate. They are frozen in position here, which means that if I took this molecule and let's say that I took that ethyl group over here and I instead pointed it downward, this is now a completely distinct molecule. All right, because again, this carbon-carbon double bond cannot rotate. So either this ethyl group is frozen up top or frozen down below, but these are not one and the same thing. And both of these, if I were to go through a name, would have that 6,6-dichloro3-heptene name to it. So we got to distinguish between these two, what we call stereochemistries of our double bond. All right, alkene stereochemistry. All right, you may have heard of cis-trans stereochemistry before, and that is used somewhat, you do see that some places, but it's not all-encompassing. And so what's preferred by that IUPAC system is what's called the E or Z stereochemistry. All right, so importantly, when we assemble our name for our alkenes, we need to include stereochemistry when necessary. All right, so first of all, that little conditional at the end there, when necessary. How do I know when it is necessary? All right, in this first example here, there was not any stereochemistry. I didn't have to worry about adding E or Z to the name. In our second example here, we do have that E or Z stereochemistry. So how am I supposed to be able to tell? All right, so if either of those sp2 hybridized carbons are bonded to two identical groups, then there's no stereochemistry. Not all alkenes will have stereochemistry if either one of your sp2 hybridized carbons, the carbon about that double bond, is bonded to two identical groups. You don't have to worry about it. So in this first example here, carbon 1 was bound to two identical groups, two hydrogens, so I didn't have to worry about stereochemistry for that particular molecule. If we look over here, that's not the case, right? Neither one of these carbons have two identical groups. All right, so how do we go about assigning E or Z stereochemistry? All right, let's put an example down here. All right, let's note that this molecule does have stereochemistry. This carbon is bound to a hydrogen in a methyl group. Those aren't identical. This carbon is bound to a methyl group and an ethyl group. Those aren't identical. All right, so if we're going to assign E or Z stereochemistry, step one is we're going to chop at that double bond. All right, so I'm going to look at this molecule and I'm going to hiya right down the middle there, chop it. And we're going to look on either side. All right, so step two is to look on either side and assign high and low priority. All right. This idea of priority is based on atomic number. So the same game that you play when you assign R and S stereochemistry to chiral centers. You got to look at those groups and assign their priority. All right. We're going to do so on the left-hand side of this double bond first, and then we're going to jump to the right-hand side and play the same game. All right. So if I look, this carbon here is bound to a carbon and a hydrogen. Which one would be my high priority group and which one would be my low priority group? Which one has the higher atomic number, carbon or hydrogen? Carbon. So that makes this my high priority group and that implied hydrogen my low priority group. Now I'm going to jump to the other side of my double bond and I'm going to play that same game. I'm going to assign high and low priority. If I look though, I have a tie. This one's a carbon and this one's a carbon. All right, so if we need to break a tie, we're going to break that tie by listing all other bonded atoms. So what do I mean by that? They're both obviously bound to this same sp2 hybridized carbon. So I'm going to list the other 3 atoms that they are bound to. This is a methyl group, which means that all 3 of its other bonds are hydrogens. If I jump up here, this carbon is bound to 1 other carbon and 2 hydrogens. And so now I see in my list here, my higher atomic number is going to break that tie, which is why this ethyl group is my high priority group and my methyl group is my low priority group. All right, so we chopped at our double bond. We jumped on the left and assigned high and low priority. And then we jumped on the right and assigned high and low priority. And the relative location of those 2 high priority groups tells us whether it is an E or Z stereochemistry. All right, so if the high priorities are on opposite sides of that double bond, this is an E stereochemistry. And if they're on the same side, that is what we would call the Z stereochemistry. Oops. Okay, so given our example above, would this be an E or a Z stereochemistry for this alkene? They're on my high priority group is pointed up over here, pointed down over here, so they are on opposite sides. So this one would be the E stereochemistry. Okay, now obviously we got to keep track of which one's which here. On opposite sides is E, on the same side is Z. How are we going to remember that? Sometimes if you can pick like the dumbest little phrase to get stuck in your head, you'll remember it forever, all right? And so for this, how we're going to remember is that our Z stereochemistry is when those 2 high priority groups are on Z, same side of the molecule. All right, if they're on Z same side, the same side, that means it's that Z stereochemistry. All right, those 3 little words will help it stick in your brain forever. All right, so then everybody take a second and just finish our name off above for this one, assigning either that E or Z stereochemistry. Yeah, and it goes in parentheses up front. Yep. I chop at that double bond. I'm comparing my carbon to that implied hydrogen. So carbon is high, my implied hydrogen is low. I jump to the other side, play the same game. My carbon is high, my implied hydrogen is low. So this would be the E stereoisomer, and we represent that by putting it in parentheses out front of that molecule's name. All right, and you can convince yourself of the other example that we got when we flipped that ethyl group. This would be the same 6,6-dichloro-3-heptene, but would be the Z stereoisomer. Right? And remember, the whole goal of nomenclature in organic chemistry is to uniquely point to a molecule. Since these two molecules are distinct, they have distinct chemical and physical properties, we would have to name them differently as well. Cool. All right, so now we're going to go back here. We're not just talking about alkenes anymore, we're talking about dienes. So now let's update our rules here for a diene, a molecule that has two carbon-carbon double bonds. All right, there's not much of a distinction here. We still have to make sure that our parent chain includes now both of these functional groups. And we're going to number in such a way that we give those functional groups the lowest possible numbers. In this case, there's only the one way to do it. Okay? When we do our name, we now have to indicate the position of both of those carbon-carbon double bonds. So this one here I would refer to by carbon number what? 1 or 2?
1.
And what about this one, 3 or 4? 3. So this would be 1, 3. I got those 4 carbons, so bute. All right, and just like when we had those 2 chloro groups, we called it dichloro. Now we got these 2 double bonds, so we're going to call it diene. But there's something missing in this name here. And we'll see this over and over again in organic chemistry, is they kind of bend over backwards to not have 2 consonants run into one another. So rather than butadiene, we're going to retain a vowel between the 2 of those. So this is not just butadiene, but butadiene. We're going to keep an A in there, so we're not running together those 2 consonants. So for our dienes, that suffix that we use is now retaining that A, diene. Right, where we specifically keep that vowel in there. Between those 2 consonants. All right. So let's do one more example here.
want us to assume easy on this one?
Yeah, so you want to be able to recognize whether or not your carbon-carbon double bond has stereochemistry. If it does, you want to assign it that stereochemistry as well. All right, so I'm going to find my longest continuous set of carbons here, those 7 carbons. That means I got that methyl substituent. I'm going to number such that I'm prioritizing those carbon-carbon double bonds. So then I get 5-methyl-2,4-heptadiene, right? I'm going to keep that A in there. And now I need to go and assign stereochemistry. And in this case, both of these double bonds have stereochemistry associated with them, right? Neither one has 2 identical groups bound to either of those sp2 hybridized carbons. So I'm going to go to this one first. We're going to play that game that we laid out, where we chop and we assign high and low priority. If I'm going to compare this carbon to this implied hydrogen, which one's my high priority group? Carbon, yes, awesome. All right, carbon's high priority, hydrogen's low priority. I'm going to jump to the other side. I got the same game. I have a carbon atom and this implied hydrogen. Again, my hydrogen's low and my carbon up here is high. So then this first double bond has what? E or Z stereochemistry? E. So those 2 high priority groups are on opposite sides. So we're going to give this one that E stereochemistry. Now we're going to go to our other carbon-carbon double bond and play the same game. We're going to chop. Over on the left-hand side, pretty straightforward, just like we've been doing, an implied hydrogen is always low compared to a carbon, which is high. But then we get to the other side, and we have a tie here. We have 2 carbon atoms bound to that carbon 5. So how do we break this tie? We got to list everything that they're bound to. A methyl group is bonded to 3 other hydrogens, whereas my carbon over here is bound to a carbon and 2 hydrogens. So which one's higher priority, ethyl or methyl? The ethyl group will be my high priority group, my methyl group, my low priority group. And now we can see these 2 high priority groups are on the same side, on Z same side of this molecule, making this our Z stereochemistry. All right. So now the last thing that we want to do is build this into our name. Since we have 2 of them, we're going to have to put them both out front, but we're also going to put the location of that particular stereochemistry. So this E stereochemistry corresponds to the carbon-carbon double bond between carbons 2 and 3, and the Z stereochemistry between carbons 4 and 5. So this is how we would build this into our name. Since there are 2 of them, we have to include the locant as well as that stereochemistry designation. All right, so 2E4Z, 5-methyl-2,4-heptadiene. Rolls off the tongue. All right, beautiful. Okay, so we have to first identify whether or not our carbon-carbon double bond has stereochemistry. So again, unless it's bonded to 2 identical groups, there's going to be some stereochemistry associated with that. And then we have to play this game here to assign our stereochemistry. All right, so now we're going to get to the other word here in the title of our chapter, our conjugated dienes. So it turns out that all the dienes in the world can be classified into one of three categories. So our classification of dienes here. All right, so we'll put down an example from each. A conjugated diene, the one we're really going to focus on in this particular chapter, has this perfect spacing of those double bonds where it goes double bond, single bond, double bond. This is what we call a conjugated diene. There's got to be exactly one single bond between those two carbon-carbon double bonds to be considered a conjugated diene. All right, if there's any more than just one, so in this example here, we're going to put these on opposite ends of the molecule. This is no longer a conjugated diene, but an isolated diene. All right, again, we have more than one single bond. Between those two double bonds. And the last one, which you really won't see very often at all, but if those two double bonds are located directly next to one another, all right, back-to-back double bonds, this is what we call a cumulated diene. And as I said, and as the name of the chapter implies, we're going to focus on these conjugated dienes. They're a very special type of diene when you have that perfect spacing of double bond, single bond, double bond. Okay? So to understand why these are so special, we got to go back to what we learned about our alkenes, specifically those carbon-carbon double bonds. All right, if we take a look at a very simple molecule, so these two carbons are sharing these two pairs of electrons, right? These are both covalent bonds here, but they're very distinct covalent bonds. The first bond is always what we call a sigma bond, but that second bond is a pi bond. All right, and the difference between these is really how we understand alkenes to be so different from alkanes as a functional group. All right, if we were to hop into our magic school bus and look at how these pairs of electrons are being shared, in a sigma bond, that electron density sits directly between those two carbon atoms. A sigma bond is exactly what you would expect a covalent bond to be. I'm sharing a pair of electrons with this other atom. That pair of electrons is sitting directly between the two of us, right? So in a sigma bond, that pair of electrons is being shared between those two bonded atoms. A pi bond is special though. A pi bond, that electron density isn't directly between those two atoms, but it is sitting above and below the plane of that atom. So in a pi bond, both of these atoms have these p orbitals, these peanut-shaped p orbitals. And it's the overlap of that peanut-shaped p orbitals that extends above and below the molecule that makes up a pi bond. All right? Alkanes, not very reactive, not an interesting functional group. Alkenes, very reactive as a functional group. So why? Because alkenes have these pi bonds, this very accessible pair of electrons, because that pair of electrons isn't tucked away between two bonded atoms, but it's sticking out above and below that molecule. All right, so much easier to get to, making that pair of electrons much more reactive. All right, so let's extend this now to our conjugated dienes. Okay, well, in my conjugated diene, about this double bond, both of these are those sp2 hybridized carbons, meaning they both have that peanut-shaped p orbital sticking out above and below the molecule. And it's the overlap of that peanut-shaped orbital that makes up that carbon-carbon double bond, the second, the pi bond in that carbon-carbon. If we go next door, we have the same thing. These two are also both sp2 hybridized, meaning that they also both have that p orbital. All right, and again, it's the overlap of that p orbital that makes up that carbon-carbon double bond, that pi bond. Okay, so why is this so special here? Well, electrons, remember, we think about them as particles, but we can also think about them as waves. And electrons will like to spread themselves out. So in this case here, this pair of electrons doesn't stay localized between these two carbon atoms, but it'll spread out into this neighboring p orbital as well. All right, so in our conjugated alkenes, conjugated dienes, these pi electrons delocalize across those four carbon atoms. All right, delocalize is a fancy way of saying spreads out across all those positions. Right? You got these p orbitals all lined up in a row. The electrons are like, sweet, I'm going to spread myself out across all four of those p orbitals. And anytime electrons can delocalize, we call that resonance. And resonance always adds stability to a molecule. So these conjugated dienes are particularly stable dienes. These are our most stable of our dienes here. All right, if we look instead at our isolated dienes, each of these pi bonds has that p orbital sticking out above and below, and it has those electrons that are overlapping to form that pi bond. All right, but these cannot talk to one another because they got this carbon in the middle here messing everything up. This carbon in the middle here does not have a p orbital available. It is sp3 hybridized. So those two sets of orbitals cannot talk to each other. Those two pi bonds can no longer talk to each other because we got this carbon in the middle messing up that network. All right, so in our isolated dienes, our pi bonds cannot delocalize. All right. And then lastly, in our cumulated dienes here, you might think that because they're located directly next to each other, that they would be able to communicate. All right, but it turns out that that's not the case, because yes, in one I have my p orbital, and in my other one I also have these overlapping p orbitals. But importantly, that carbon in the middle can't have those p orbitals parallel to one another. So that second set is sitting perpendicular. So again, even though they're back to back, those pi bonds cannot delocalize. All right, and in fact, cramming them back to back and parallel to one another actually raises the energy of that molecule. So out of all of our dienes here, these cumulated dienes are the least stable. All right. So when we're talking about our stability of dienes, all right, this is where we're going to pick up next class period, but the most important factor is whether it's conjugated versus isolated versus cumulated. All right, there's two other factors that will play in here that we discussed last semester with regard to just alkenes in general, and that is what we call degree of substitution. And then lastly, that stereochemistry that we discussed today. And we'll see examples of that next class. What up?
Questions on the, like,